Okay, so this is the third video in our sequence of videos on transformations, and in the last video we introduced applying transformations from first principles. So first of all, thinking about what happens to the point, every point on the graph, and working out how to then apply that to the function. What we want to do in this video is reverse that process. So we want to determine the sequence of transformations using our first principles approach. And so it is really literally just reversing what we just did in the last video. Okay, so the first thing that we want to do is make sure we identify which is the image function, so which is the endpoint, and label the x and y in that function with x dash and y dash. Okay, it's important that we get that right, or else everything will be backwards before you start. The next step is to rewrite both functions so that they have the same shape. I'll talk loosely about that, but let's say, your original function is y equals x squared. Then you want your image function to be something involving y dash equals something involving x dash all squared. Okay, so it still needs to have the same shape. If your original function is y equals root x, then your other one needs to be something equals square root of something, with x dashes in here and with y dashes in here. Okay, if your original function is y equals 1 on x, then your when you rearrange the image functions to get them in the same shape, you want something involving y dash to be equal to 1 over something involving x dash. So you want to get them in the same shape. I know that's a loose instruction, but we'll see that executed. And then once you've done that, you should be able to see the substitutions that were made. You should be able to see what x is equal to and what y is equal to, and get back to those two little equations. Then we're actually trying to work our way back to what is the image point. Okay, we want to know what is x dash and y dash. So you want the image of x, so x dash and y dash, to be the subject of your two little equations, and then you want to be able to interpret the transformations from that point. Okay, and all that requires is a good understanding of your order of operations. Alright, so let's just kind of work through that. So the first thing is we've got y equals 1 on x squared maps to y equals, so this is the image, y dash equals 3 over x dash minus 5 all squared plus 6. Okay, so our original function is a truncus, so we want to be able to rearrange this. So we've got something to do with y dash equals 1 over something to do with x dash squared. Okay, which means that this plus 6 needs to go onto the left hand side, and this 3 needs to go onto the left hand side, because the right hand side has to be just 1 over something involving x dash all squared. Okay, so we focus on that first. We take away 6 from both sides, which gives y dash minus 6 equals 3 over x dash minus 5 all squared, and then we divide both sides by 3. So y dash minus 6 over 3 equals 1 over x dash minus 5 all squared. Okay, so now we can see if y equals 1 on x squared became this function here, we can see that y was replaced with y dash minus 6 on 3, and we can see that x was replaced with x dash minus 5. And we can get back to our two equations. So y equals y dash minus 6 over 3, and x is equal to x dash minus 5. Now, it's important that you keep your eye on what you're trying to do. So when we're applying functions, we want to have x and y as the subject of our two equations so that we can substitute in. When we're determining the sequence, we're trying to work out what was the image of x and what was the image of y. These are what we want to know. So we want the image of x and the image of y to be the subject of the equations. Sometimes that doesn't require any rearrangement, so I don't want you to automatically get into the pattern of, here's my two equations, then I rearrange them, then I've got my answer. I want you to focus on what it is that you need to be the subject of the equation. And in this instance, we need x dash and y dash to be the subject. So 3 times y is y dash minus 6, and therefore y dash is 3y plus 6. Here, x dash is going to be x plus 5. Okay, and so that means that our point xy became the point x dash, which is x plus 5, and y dash, which is 3y plus 6. And now to list off the sequence of transformations, this simply requires you to understand order of operations. Now, the transformations that apply to the x coordinate don't have any effect on the transformations that apply to the y coordinate. Okay, so we can list the x transformations and the y transformations in any order that we want. Okay, let's focus on the x variable first. So all that's happened to x is we've added 5 onto it. If we add 5 onto all the x coordinates, that is a translation to the right by 5 units. Okay, remember it's about the point. You've got a point, you've added 5 onto its x coordinate, you've moved it across to the right by 5. Okay. Then let's focus on the y variable, and this is where order of operations is important. The first thing happening to y in this expression is it gets multiplied before we add on 6. So therefore, the multiplication, that dilation, needs to be explained first, needs to be listed first. Dilation by a factor of, so if the y coordinates get multiplied by 3, we're stretching by a factor of 3 in this direction, that is from the x-axis. Dilation by a factor of 3 from the x-axis, and then we add 6, so then we translation up by 6 units. So that is a correct sequence of transformations. As I said, this yellow transformation, the one that affects the x coordinates, can happen in any order relative to the 2 that affect the y coordinates. So that translation could be listed in the middle there, and that would also be perfectly correct, or that translation could be listed at the end there, and that would also be perfectly correct. What is important, that out of these 2 translations listed in green, that one happens first and that one happens second. If those 2 green transformations are out of order, if you list that translation up by 6 before you list the dilation by a factor of 3, then you've got the wrong sequence. Again, there could be other transformations as well, because this expression, 3y plus 6, could also be written as 3 times y plus 2. And in that instance, the first thing happening to y is add 2. So you could say translation up by 2 units, and then dilation by a factor of 3 from the x-axis. That would also be a correct sequence. So there's lots of correct sequences that you could list that you can see a bit more clearly and flexibly from this format compared to function notation, which really restricts you to Dr. T, dilation, reflection, translation. Okay, so it all depends on how you choose to write this in terms of how you're going to the correct order. As I said, if you wrote that same expression in this format, you would list the translation up by 2 first, then you've dilated by 3 from the y-axis, and that would be correct. So in that case, you could list the translation before the dilation, but it wouldn't be a translation of 6 units. It would be a translation of 2 units. Okay, so just being really clear about the fact about the order of operations that are happening in these expressions for x and y. All right, let's have a go at another one. Determine a sequence of transformations that maps y equals x cubed onto y equals half times 4 minus x all cubed minus 1. Okay, so we're going from y equals x cubed to y equals, so it's really important that you're clear about which is the image, which function you're going from what to what. Okay, so it's 4 minus x all cubed minus 1. Okay, so this is the image on the right, this is the resulting function, so that's the x dash and the y dash. Okay, we want to get them in the same shape, which means we want something to do with y dash equals something to do with x dash all cubed, nothing else. So anything outside of the cubed bit on the right actually is affecting the y coordinate and needs to go to the other side. So that is this minus 1 and that is this half. So we want to rearrange this a little bit. So I'm going to add 1 to both sides. Y dash plus 1 equals half times 4 minus x dash cubed. And then we're going to double both sides to get rid of that half. So it's 2 times y dash plus 1 equals 4 minus x dash all cubed. Okay. Alright, so now we can see the substitutions. Y was replaced by that, and x was replaced by that. So we can get y equals, sorry, I should have written a bit smaller, 2 times y dash plus 1. And you can expand that out if you prefer, that's fine. Again, you just get a slightly different looking expression at the end, and therefore a slightly different sequence of transformations described. And x is equal to 4 minus x dash. Now remember, we want to know what is x dash and what is y dash, and so we want to make x dash and y dash the subject. So I'm going to halve y on 2 equals y dash plus 1 and take away 1. So y on 2 take away 1 Or that could also be written as half, so it could also be written as y minus 2 all over 2. Okay, and you're going to describe a slightly different sequence depending on which of those you use, but both will be correct. If we make x dash the subject here, I'm going to add x dash onto the left and take away x. Sometimes it's easier to think about that as minus x plus 4. Again, you could also say that's minus x minus 4 if you want to describe it differently. So it really does depend on how you end up with the answer written. Alright, sorry, I haven't left us a lot of space here. So what we've learnt here is that the point xy became x dash, which is negative x plus 4, and y dash, which is, I'll go with my first one, y on 2 minus 1. Okay. Alright, so now we want to read off our transformations by looking at what's happened to each point. So the first thing happening to x here in the x coordinate is that x has been multiplied by negative 1. So that is a reflection. If you make the x values negative, a reflection in the y-axis. Sorry, yes, in the y-axis. And then we've added on 4, which if we add 4 onto the x coordinates, we are translating. So translation to the right by 4. So that's the two transformations affecting the x coordinate. Please note that if you had written this as negative x minus 4, then you would have translated to the left by 4 before you reflected in the y-axis. And that would also be a valid and correct sequence of transformations. Okay, but again, the order is important. If you're going to list the translation first, it's a translation to the left by 4, then then a reflection in the y-axis. If you list the reflection first, it's got to be a reflection in the y-axis, then a translation to the right by 4. Okay, both of those would result in the same answer. And if we're looking now at the y coordinate, y has been halved. First of all, y on 2, remember, is half of y. So we've multiplied all the y coordinates by a half. So that's a dilation by a factor of half from the x-axis. If we're multiplying the y coordinates, that is from the x-axis, okay, or parallel to the y-axis. And then we've subtracted 1, so then we've done a translation down by 1 unit. Once again, if we'd written this as y minus 2 all over 2, we would have translated down by 2 units before we then did the dilation by half, because that would be half times y minus 2. Translation down by 2, then dilate by half. Okay, so more than one way to describe each of these pairs of transformations, and then equally the transformations affecting the x coordinate, the order within those two is important, but they can be combined together with the transformations affecting the y coordinate in any order. So we could list it as 1, 2, 3, 4 if we want. We could list it as, 1, 2, 3, 4 if we want. We could make it the two y ones first, 1, 2, 3, 4, okay? As long as this happens before this, and this happens before this, the order can happen in any other way, okay? So we can jumble together these, you could have a yellow and then, so we could have, we couldn't do that one first, 1, 2, 3, 4, okay, whatever it might be. And sometimes you might write it that way because you might like to always list dilations and reflections first and then translations, but you don't have to. This is perfectly correct as it is. Okay. And obviously also then you've got the alternative ways that they could have been described, but still thinking about the different ways you can combine them together. So you don't need to list all the different sequences, you just need to be able to list a correct sequence of transformations. But also just my point is that don't be alarmed if the answer is slightly different. I want you to be able to think back to this and think, would that sequence given in the answer still result in the correct expression for the image of x and the image of y? Okay, example 3, I thought it might be the last one, but we've got a couple. Okay, so this time we want to determine a sequence of transformations that maps this to this. So this time we're going from the messy function to the nicer function, and this is actually an easier process as long as you keep your eye on what is it that you're trying to do rather than just blindly following process. Okay, So we're going from y equals negative 2 times root 3x plus 1 to y equals root x. So this is the image function. There's the dashes there. We need them in the same shape. It's a square root function, so it has to be something to do with y dash equals the square root of something to do with x dash. So anything outside of the square root on the right hand side needs to be moved onto the left, which is that there. So if we divide, need a pen. If we divide by negative 2, y on negative 2 equals square root of 3x plus 1. Okay, so now we've got them in the same shape. We can see that this expression here was equal to y dash, and this expression here was equal to x dash. Okay, so y on negative 2 equals y dash, and 3x plus 1 equals x dash. Now this is where it's really important that you keep your eye on what it is that you're trying to find. So if we're trying to apply a sequence of transformations to a rule, we need x and y to be the subject so we can substitute in. If we're trying to determine the sequence of transformations, we are trying to work out what is x dash and what is y dash. So we want x dash and y dash to be the subject. Now, when you're going backwards from a messy function to a nice function, automatically when you write down these equations, you have y dash and x dash as the subject. So you don't need to rearrange the equation. So this is where I want you to try and move away from just thinking, oh, I get two equations, then I rearrange them, then I do this with them. Think about why you're rearranging them, what the point of that is, because in this instance, we don't need to rearrange them. We already have x dash and y dash here. So x dash is 3x plus 1, and y dash is negative y on 2. Okay, I might write that as negative half y. Now I can read off my sequence of transformations. So looking at the x coordinates, the expression is 3x plus 1. So x has been multiplied by 3 first. So that's a dilation by a factor of 3. If we're multiplying the x values, we're stretching out this way, which is from the y-axis. Okay, then we've added on 1 to the x coordinate, so that is a translation up by 1 unit. Then looking at the y coordinates, we've got the negative, so negative y values. And if we've made the y coordinates negative, we've flipped it around the x-axis. Okay, so that is a a reflection in the x-axis. And then we've multiplied the y values by 1/2, so we have done a dilation by a factor of 1/2 from the y-axis. Sorry, not from the y-axis. The y coordinates have been multiplied by 1/2, so that is from the x-axis. Okay, once again, these two statements are affecting the x coordinate. These two statements affect the y coordinate. We can then combine those together in whatever order we want. We could list the y ones first, 1, 2, 3, 4, or we could jumble them up together as long as that 2, 3, 4, as long as the order within the x and y coordinates is still consistent. We could, go to, we could do, whatever we want. We could go 1, and then we could list both of these, 2, 3, and then come back to this one, 4, whatever order you would prefer. Okay. The other thing to note is this, we could, if we really wanted, write that as 3 times x plus a third, in which case we could talk about translating to the right by a third before we do the dilation by a factor of 3 from the y-axis. Either of those, sorry, that's not up, is it? It's to the right. Sorry, it's an x coordinate. Alright, so again, a number of different ways that you can describe it. Just make sure you give a correct sequence. The question will never say determine the sequence of transformations because there isn't a definitive sequence. It'll say determine a sequence of transformations. Okay, I suspect this is our final example. Yes, let's have a look at this one. Determine a sequence of transformations. So this time, in the previous example, we went from a messy function back to the neat function. Here we're going to go from a messy function to another messy function. Now these last two examples are where if you're working in function notation, these get really difficult. Okay, if you're working in function notation, you kind of need to work out what transformations take me back to x squared and then what do I need to get there. But in this process, we don't need to do that. The process is identical. Okay, we are going from y equals 3x squared plus 5 to y equals 2 times 3 minus x squared plus 4. This is the image. Be clear about which one's the image, which one are you going to, and then we want to get them in the same shape. So they're quadratic functions, so we want something to do with y dash equals something to do with x dash all squared. Okay, so anything outside of the squared needs to go over onto the left hand side. So in this case that's the times 3 and the plus 5. In this case that's the times 2 and the plus 4. So I'm going to take away 5 and then divide by 3. And here I'm going to take away 4 and then divide by 2. Okay, so now we can see the substitutions. That is equal to that, and that is equal to that. Oh, sorry, I put a dash instead of a squared over here. Okay, so now we know that y minus 5 over 3 is equal to y dash minus 4 over 2. Okay, and we also know that x is equal to 3 minus x dash. Now we're trying to determine the sequence of transformations, so we want to know what is x dash and what is y dash, so we want to make x dash and y dash the subject of these two equations. Alright, left hand side, if we cross multiply, which is essentially getting a common denominator of 6 and then multiplying by 6, we get 2 times y minus 5 equals 3 times y dash minus 4. So that's 2y minus 10 is 3y dash minus 12. We're making y dash the subject, so let's add 12. That's 2y plus 2 equals 3y dash, and divide by 3, so 2y plus 2 over 3. Or we could write that as 2/3 y plus 2/3. The x is a bit easier, so if we take away 3, x minus 3 equals negative x dash, and then multiply everything by negative 1, x dash is negative x plus 3. Okay, so xy becomes the image of x, which is negative x plus 3, and the image of y, which is, now personally I'm going to go with this version, because if I use this one, you can, but if you use this, when you're going to describe these transformations, which is essentially you're doing this, okay, you've got a dilation from the x-axis by a factor of 2, then a translation up by 2, and then another dilation from the x-axis by a factor of 3. So it's better, I think, to expand it out and only have to describe one dilation from the x-axis and then one translation. Okay, so personally, it's not incorrect, but it's just a bit of a cumbersome sequence of transformations if you're describing two separate dilations from the x-axis in two different places in the sequence. Okay, so now we can do our list out our transformations. So focusing on the x coordinate, first of all, x has been multiplied by negative 1, so that is a reflection in the y-axis if you make the x values negative. Then we're adding 3 onto the x coordinate, so that is translation to the right. Translation to the right by 3 units. Then we've got the 2/3 times y, so we're multiplying all the y coordinates by 2/3, which is a dilation by factor of 2/3 from the x-axis. If it's the y coordinates that are being multiplied, you're stretching away from the x-axis. And then we've got the plus 2/3 at the end here, which is adding 2/3 onto the y values. So that is a translation up by 2/3 of a unit. Okay. So once again, you've got your two transformations that affect the x coordinate and your two transformations that affect the y coordinate. They can be put together, jumbled up in any order, as long as the order within the yellow ones is still the same and the order within the blue ones is still the same. Okay, so the work today, apologies, is from, again, a worksheet at the back of your booklet in Appendix F, determining the sequence of transformations using first principles.